All right, so perfect. I'd like to introduce Tom Maccarone, who will be speaking with an invited talk on lags and reverberation in X-ray binaries.
Okay, so I'd like to thank the organizers for inviting me to give this talk, and I really wish I could be in Cagliari with you all, but you know how things are these days. So I'm going to talk about some of the motivation for understanding lags, some of the methods for studying lags, and some issues that deserve some special attention to make sure that you're interpreting things properly. Because of upcoming talks by Alex Teterenko and Abby Stevens, I'm going to say very little about long wavelength lags from jets or software choices for doing the computations. And since there's some applications talks that are coming up directly after mine, I'm going to talk more about the philosophy of why and how these measurements are made, and less about results that have come out of the measurements. That was just because this is a limited amount of time, and I thought it'd be better to focus on things that give everyone a general understanding of what's coming up later in the meeting. All right, so first, motivations for timing studies in general. So a lot of it, I remember hearing in graduate school somebody telling me that astronomy became astrophysics when people first started taking spectra of things. And spectroscopy has been one of the workhorses for understanding astronomical objects for generations. But if you think about the assumptions that are made in doing spectroscopy, usually you're assuming that you have an optically thick, homogeneous, and spherically symmetric system that you're looking at. And all of those assumptions are violated for most of the kinds of things that we're talking about at this workshop. Right, so you have an accretion disk, which has a variability in temperature, probably getting hotter as you go inward. It may have multiple components emitting in certain parts of the spectrum, like a jet or a disk wind. And then you also have a companion star sitting here. So all of your basic assumptions for using spectroscopy are troublesome. Secondly, if we think about the sun, which is probably the astronomical object we understand the best, the solar spectrum was one of the first spectra of anything obtained. And we've had gory detailed solar spectra for generations. But it wasn't until helioseismology came on that people really developed a deep understanding of the solar interior. And so when we have objects that have, and something similar is true for the interior of the Earth, we understand that better from earthquake data than from any kind of measurements we can make of the surface of the Earth. And so if you want to understand things in detail, variability studies give you much better information to go after that. All right, so next I want to talk about the degeneracies that you can get from spectroscopy. So even if you have good spectral models, often you won't be able to understand the spectra in a way that can be definitive. And these two plots here show, these are different sources. This is Cygnus X1 and this is XCE J1118 plus 480. And they're plotted in different ways. This is plotted in E squared DNDE, and this is plotted as F nu. But if you look at what the spectra look like in the X-ray band for these two sources, they're very similar. And yet this model is based on Comptonizing corona, and this model is based on synchrotron emission. And the issue is that the spectra of X-ray binaries in the X-ray band are often quite simple, so that you basically have a gamma of 1.5 to 1.7 power law, and you can find a variety of theoretical models that will produce that. And these jet-based models have gotten a lot more complicated over the years, but still what they're basically producing is a gamma of about 1.5 to 1.7 power law. Right, and so just from the spectra, you really can't figure out what's going on with the accretion flows in these systems. You need some other kind of information. And then this plot on the right, there's a figure from Fragile, Miller, and Van der Noot 2005, where they consider the possibility of a tilted accretion disk and think about what that does to the iron line profiles that you would get from a system. And then there's some more recent work by Abar and Kravchinsky that came out earlier this year that does this kind of thing in more detail. And what you find is that often it's hard to distinguish between a planar disk and a tilted disk just from looking at the iron line profile. So again, what you want to do is look at some other kind of information that might help break those degeneracies. All right, so I want to talk about power spectra versus lags as ways to approach what's going on in a system. These are the two main techniques that are used for probing variability, although I would say in the past decade or so, a bunch of more sophisticated techniques have started getting used a lot more often. So power spectra are really good for determining what's happening at a few key locations in your accretion disk. For example, if you get QPO frequencies or if you get break frequencies in the power spectrum. But after decades of studying power spectra, there's still a lot of debate about what the interpretations are, which suggests that we need more and better information to probe what's really going on. Lags can help calibrate power spectral techniques and help map out the whole accretion flow, because if you could get different models that predict the same power spectrum, but very different lag spectra. All right, so first of all, now I want to talk about the techniques. So first, measuring lags from time series. So there's a couple approaches that you can use. There's the cross correlation function, which is a time domain approach, and the cross spectrum, which is a Fourier domain approach. In principle, the same information identically is contained in both of these types of data, but they can be useful in different ways for what they draw your attention to. So both of these have some nice properties. The cross spectrum has been used more widely in X-ray binary studies, whereas the cross correlation is used a lot more in many other astronomy applications. And I'm going to talk about both of those and a few other things related to them. All right, so cross correlation functions. So this is the algebraic form of the cross correlation function. If you know the functional forms for the functions that you have. So essentially what you do is you take two time series, you add a time lag tau you add time lag t to one of the series, and then you integrate over all values of tau, and then you get a correlation as a function of t between these two functions. This is a graphical illustration of what's going on there. Now, for actual data, there are a couple of different discretized versions of this that exist. There's Edelson and Krolik's discrete correlation function. And then in about a decade after that came out, Tal Alexander proposed the Z-transformed discrete correlation function. And essentially, these have different approaches for how to deal with unevenly sampled data and sparse data sets. Alexander's approach basically calculates a Z-score for each data point, whereas Edelson and Krolik just do standard measurements of the correlation coefficients based on the actual fluxes that you measure. The Alexander approach seems to work better for very sparsely sampled data sets. And if you have really good data, probably it doesn't matter so much which technique you choose. All right, cross spectra. All right, so for the cross spectrum, what you do is you compute the Fourier transform of both of the time series that you want to look at. You then take the actual Fourier transform of the time series in one band and multiply it by the complex conjugate of the Fourier transform of the other band's time series. And when you do that, you cancel out the phase information due to the arbitrary choice of the start time for your time series. And the phase that's left behind is an actual phase lag between the two time series. And so you can then take the arctangent of this quantity here and get an actual phase out. All right, so then, right, okay, and so this is strictly equivalent to the cross-correlation function in terms of the information contained, because by the convolution theorem, you can essentially say that one of these is the Fourier transform of the other one, but it presents the information in a different way. The previous one, you get a set of correlation coefficients as a function of time lag. And here, for every Fourier frequency, you get a different phase lag. And if, for example, you have a strong oscillation within your data set, you can isolate the phase lag of the oscillation relative to the phase lag of the noise processes. Okay, so now I want to talk about the cross coherence. So the cross coherence, what you do is you take the cross spectrum and then you take the square of its mean value and you divide by the product of the of both power spectra. All right, and you do this as a summation. And so what you're doing essentially is you're estimating how consistent the time lags, the phase lags are. And this is a nice illustration from a paper by Mike Novak from 1999, that if you have perfectly coherent data, the phase lag is the same for every little chunk of the time series that you look at. If you have perfectly incoherent data, you get random measurements, and eventually this coherence goes towards zero. And if you have partial coherence, then this thing increases in the sense that there's a component that's always pointing in the same direction, but it doesn't give you the same as a perfect coherence. So you get a number between 0 and 1 with a bias based on the number of samples that you have. So if you have a very small number of samples, you can't measure this very accurately. But with a very large number of samples, then you can measure this precisely, and it'll tend towards 0 if the phase lags are random. It'll tend towards 1 if the phase lags are exactly the same every time. And it'll be somewhere in between if the phase lags are mostly the same, but have some real variations. All right, and this is somewhat related to the normalization of the cross-correlation function, but there's not a one-to-one correspondence. And with using the cross-coherence, you can isolate whether, for example, the phase lags within your oscillation or your QPO are always the same, but the phase lags in the red noise component vary, or the opposite. All right, so the relative values of these two approaches. So the cross-correlation function is really useful if you have the same time series in both energy bands just shifted, and you might get that, for example, if you had a thin ring that you were reflecting off of and just adding a certain time delay from that, but otherwise you were producing the exact same time series in both cases. The cross spectrum is much more useful for probing complicated geometries because it lays out the lags in a useful manner for understanding how they're varying as a function of frequency. All right, now I want to mention something called the transfer function. And this is something that people used to talk about a long time ago. And for Agn reverberation mapping, with apologies to Mike for using the terminology, this is still often talked about, but people, I think, have kind of forgotten about measuring this directly. All right, so this paper by Blanford and McKee, 1982, they talked about what is called Agn reverberation mapping, where you have a continuum source at the center of an Agn accretion disk, and then that excites an emission line somewhere further out in the accretion disk. And by probing the response of the emission line to the changes in the continuum, you can try to understand the structure of the accretion disk. And it's also often used to estimate the masses of supermassive black holes. And so the idea here is you take the luminosity in the line as a function of velocity and time, and you set that equal to some integral here over t prime of the luminosity in the continuum as a function of t prime times some psi of velocity and time lag. All right, and the psi is called the transfer functions. So if all of the lags are due to light travel, then the transfer function will give the geometry. And the transfer function can be written in this manner, that it's equal to the inverse Fourier transform of the power spectrum here divided by the emission lines power spectrum divided by the continuum's power spectrum. And the emission lines is taken as a function of velocity. All right, so often this is talked about, but it's never computed directly. And for the initial Agn reverberation mapping problem, it's probably not practical to ever compute this directly. But I've been thinking that X-ray binary continuum with things like really bright sources with NICER, and almost certainly with future missions like STROBE-X and EXTP, we may actually be able to directly compute a transfer function using this equation here and actually just inverting this, because we may get such high signal and noise that we don't really have to worry about the noise messing this up. So the reason that people use more indirect methods to estimate the transfer function is that if you start dividing large amounts of noise by large amounts of noise, you get something that doesn't make any sense, and then you can end up including that in the transfer function. With things like EXTP and especially STROBE-X in the future, we may get such high signal and noise unvariability in certain cases that we could go and directly compute transfer functions. And I think that's something worth keeping in mind going forward. All right, so now I want to talk about the physical mechanisms for making lags. So one is reprocessing. And so the idea here is that you have some continuum source, it illuminates an accretion disk, and then that emits some emission line typically, but it could also be continuum in a different waveband. And then the observer will see the direct emission from this region follow this path length, and the indirect emission from the different other regions follow these other path lengths, all of which are going to be longer than this path length. And so the light travel times increase, and this can lead to lines and parts of the continuum showing lags. Okay, and so in most cases in X-ray binaries, light travel times probably dominate over other parts of the reprocessing process, but this doesn't have to be the case. And then the other issue is that the corona doesn't need to be point-like or lamppost-like. It could be some much more diffuse source of emission so that you get some multiple lags that you really have to be considering in order to interpret the data. Okay, so another possibility of propagation models. So in this case, if we have a temperature gradient and some kind of front moves through an accretion disk, it starts in the cooler region and moves into the hotter, higher emissivity regions. And so whatever this front is doing, it probes the coolest regions first and the hottest regions last. And that can lead to time lags where the hard X-ray emission lags behind the soft X-ray emission. And the emissivity index would probably also increase as you do this because of the temperature changes. And so that's another method for producing lags that's often talked about. All right, and finally, intrinsic changes in the system can also lead to production of lags. All right, so one thing is that thermal reprocessing should take longer than light travel times. If you look at this thermal time scale, if you take kind of the standard equations from Frank, King, and Rain, you get the light travel time divided by alpha times R over RG to the 1/2 power. Alpha is less than 1, R is bigger than RG. So the thermal time scale should be larger than the light travel time scale. What probably is actually going on in most cases is that the reprocessing is happening in a very thin skin at the top of the accretion disk so that it doesn't have the full thermal time scale of the whole accretion disk. And if you got photons to go through the accretion disk all the way to the midplane before they get absorbed and reprocessed, they would have this long lag. And this is something I think hasn't really gotten as much attention as maybe it should. Now, other intrinsic mechanisms is you could have magnetic reconnection or soft heating in the corona that may have their own timescales for accelerating particles that could be longer than the light travel times. And these are most likely to affect the non-thermal parts of the spectrum. And then the other thing that I think is Phil mentioned in the Slack chat, and that I think he and Julien have a poster about, is that you can get cases where external photons from the accretion disk go into the corona and change the heating and cooling balance in the corona so that you can change the temperature of the corona on some time scale that's related to what's going on somewhere else. And I'm not sure whether we should put this here or in the reprocessing section, but it's something that can certainly be going on that may produce interesting lags. All right, so a couple things that I think are worth paying attention to. One is that many processes can happen at once. So this is from a plot from Gierlinski et al. 99. You can see this is a typical reflection spectrum. This is our accretion disk and our corona here. And if you look at this, the emission line from which you might look for lags due to reflection is way below the continuum here. So typical equivalent widths of iron K alpha are around 200 to 300 electron volts. The physical widths are typically of order keV, and that means that the continuum dominates in that band. You also get things like K beta can blend with K alpha, so you have more than one line present at any given energy. So you really need a full understanding of the continuum lags and the atomic physics present in order to make a detailed interpretation of reflection lags from emission lines. Now, with good enough data, you can end up having an enormous number of constraints. Different emission lines have different ionization states and may come from different parts of the disk. And so if you go and measure everything really carefully with good enough data and good enough models, you can really solve everything that's going on in the accretion disk. So that's why the promise of this technique is so great. All right, next, lags must be interpreted in a bigger context of other constraints. So I'm thinking back to when I was doing my PhD thesis, what people knew is that there were hard lags in the hard states of X-ray binaries, and that they had log energy dependence for the lags. Now, this log energy dependence for the lags is exactly what you would predict from light travel times. If you had a big puffy quantizing region and photons kind of diffused out of it. That if you had your energy would depend on the number of scatterings that you had, and the number of scatterings that you had would determine the time lags. And if you work through the math for that, for typical coronal geometries, you would expect a log energy dependence for the lags. And it was found. And that gave a lot of credence to the idea that those lags were produced by a lot of scatterings. Now, what we did, and what can also be kind of dug out of a paper by Lin et al. That come out a little bit earlier than our work, is we looked at the autocorrelation functions of Cygnus X1 as a function of energy. And what we found is that the high energy autocorrelation functions were narrower than the low energy autocorrelation functions. The conclusion that you can draw from that is that whatever processes are producing the high energy photons, they have to be faster than the low energy photons. And so it can't be some kind of diffusive upscattering. It needs to be something more intrinsic to the system. All right, so over time, people have come around to the idea that propagation models do a good job of explaining this. Now, if you want to see a good example of how to approach considering lags and power spectra together using modern frameworks, I think Alex will be talking about that in her presentation. All right, so my summary and conclusions. Timing measurements and especially lags have the power to disentangle more physics than spectral energy distributions or power spectra alone, but they still must be interpreted in the broader context of all the other available data for the source in order to make the best measurements. And I hope I aimed right by aiming for about 20 plus 10. Although Greg just gave me the 4-minute warning, so maybe I was supposed to do 25 plus 5. But I hope people have some questions.
All right. Well, let's thank Phil, or thanks Phil. Let's thank Tom for the first time. And then I will open it up to questions. I see the very first question is from Phil, and there was also a comment in the Slack channel as well from Phil, so you guys should check that out.
Oh yeah, no, I was just kind of a grumpy comment that transfer functions are called impulse response functions by signal processing people. It was just Blanford and McKee got that wrong. But
okay.
Anyway, I just wanted to kind of maybe correct you a little bit that with the transfer function, aka impulse response functions, yeah, it is very difficult to kind of deconvolve those and reconstruct them kind of, I guess, you know, in a non-model dependent way, right, from the data. But what people are doing a lot more of now is forward fitting those. So it's kind of like the problem with spectral fitting, right, that you have the instrument response, and now we actually have some kind of impulse response function, which is a convolution that you're applying to the time series. And you can do that with the lags. And I think that's probably the best chance that we've got until we have like 100 square meter X-ray detectors or something.
Yeah, I think it'll be interesting to try this out with bright sources when we get the next generation timing instruments. You might be right about that. I haven't done a bunch of simulations to see how bad the noise gets. But the one thing I would say is the one difference here is that with spectral energy distribution fitting, the response matrix isn't diagonal. So inverting it and directly fitting the real spectrum just isn't possible. Whereas here, there isn't a non-diagonal thing that you have to get rid of in order to do stuff. And so that's why I'm a little bit more optimistic about this for not having to do forward fitting at some point in the future when we get higher signal and noise. But if you've done some simulations and you think 100 square meters is what we need, then I would tend to trust you.
Yeah, well, we tried to do it with Loft, but you just get killed by the noise. I think it's just the fact that you've got very weak low amplitude variability as well at the high frequencies that you really need to pull out the, the real light travel signals.
Okay, so you think even like SCO X1?
Challenging. I think you're okay if you have large amplitude variability and large time delays. Like if you're looking at, say, reflection off the companion star, that might be interesting.
Yeah. Okay.
Are there questions? I'm not seeing any in Slack. Are there questions in the room?
No questions for the moment.
All right, then I'll use the chair's privilege to ask a question.
Okay.
So you alluded to this a little bit, but we have lots of correlated information by the fact that we've got multiple different frequencies where we can actually measure these lags. Electromagnetic frequencies. And my question is there, a particular tool that you think would be the best way of approaching that sort of wealth of information and to try to tease out what's going on, not just in, one frequency compared to another, EM frequency compared to another, but across wide bands.
Okay, so you're talking about continuum or narrow features first?
So I'm just thinking in general that there's a lot of interdependence, whether it's actual statistical interdependence, but more importantly, physical interdependence of the data across electromagnetic frequency, and that might give us more leverage, which you alluded to in your talk, on figuring things out.
Yeah. Okay. So if you impose, I don't know if that's like a question that has like a clean answer, but I'll try to talk about the issue. So I think if you look at things like what Alex Tedorenko is probably going to talk about in a couple hours, where you have a model and it makes predictions in a bunch of bands, and then you figure out which set of parameters agrees best with all of the different bands, then yeah, in that kind of case, I think the forward fitting approach that we were talking about before is probably the best we can do right now. Because but it becomes model dependent at that point, right? So so I think it's just kind of one of the most general problems that we have in almost any kind of data analysis, that you can fit things better if you impose a model on it, but then you don't know 100% for sure if your model is correct. So I don't know if I really said anything useful there, but we got a couple other questions popping up now.
That's fine. Federico.
Hi, very, very nice talk. I really enjoyed it.
Thank you.
I wanted to understand better. So the problem in the convolving, maybe this is a question for Phil, is just that at the frequencies where, let's say, the amplitude is playing is not enough for all the X-rays. So as maybe Phil said, for multi-wavelength.
So if you go here, this is what I think we're talking about, this equation here and trying to actually use this, right? So this is, I copied the equation in the form that Blanford and McKee had it, where it's emission line as a function of velocity and omega, but in principle, these could be two different continuum bands, right? Mm-hmm. And you're looking for this impulse response function between them. And so you're taking one Fourier transform and dividing it by another Fourier transform, right?
Yeah.
And so if you have substantial Poisson noise in there, in either of the two bands, but I would say probably especially in the denominator, you can end up putting a component in there that's a big noise component. And then you take the inverse Fourier transform of something that includes a big noise component. So essentially what you need is for
you cannot subtract the noise at that point.
Right. Yeah, you can't subtract the noise you can subtract the noise from the power spectrum, but you can't subtract the noise from the Fourier transform. Right. So I think that's kind of the fundamental problem there. But if you get enormous signal and noise on the variability, then you don't necessarily care about that.
Okay, great. Thank you very much.
All right. I'll go back to see if there's a question from the room.
Demis Kazanis has a question, I think.
I know. I'll go back. I'm just trying to go back and forth.
Oh, okay. Okay.
Still no question.
Gotcha. Yeah. All right. So Demosthenes.
Okay. Good to see you, Thomas. You mentioned the inflow model for the lags, which is sounds perfectly reasonable. The question is, for a thin disk, the inflow timescales are extremely long compared to what at least I have in mind. Do the lags are consistent? The absolute value of the lags. I mean, clearly the direction is correct, but the absolute value, is it consistent with flow in thin disk?
No, but this model is applied to cases where it's probably some kind of geometrically thick disk, not thin disk. It's applied to hard state systems.
Okay, so are those timescales consistent with the observations?
Yeah, they're reasonable. I mean, you have to know what alpha is, and you have to know what H over R is, but they're not unreasonable.
Okay, so you take H over R1 if it's thick. So
yeah,
you have to put in. So you have to get a value for alpha from that.
Right. Yeah.
And
you also don't necessarily know exactly what the radii that you're probing are, but the numbers are, you can come up with reasonable values for the outer radius of the hard emission region and alpha that match reasonably well to the lags that are observed. But I think we need new approaches to figure out how to break the degeneracy between which of those is which and make sure that the model really is correct.
Fair enough. Thank you.
think that's a great time to shift any other questions we have onto Slack. And let's thank Tom again for his presentation.